Mollah, and speaker Dr. Rakesh Matham, IIIT Guwahati, to come over the dais and take your seats. We have with our next session chair, Dr. Ayatullah Faruk Mollah, Assistant Professor and ex-head, Department of Computer Science and Engineering, Alia University, Kolkata. Dr. Mollah is an active researcher in the field of data science, deep learning, computer vision, and bioinformatics. He has authored nearly 100 articles in referred journals and conference proceedings. He received several national and as well as international awards for his research contribution. Now I request Sir to come over the dais and introduce our key speaker for today.
A very good morning to everyone present over here. Today is the first day of the International Conference on Data, Electronics and Computing. And the conference is being held in a beautiful campus near home, and in a city whose landscape is very nice, very enjoyable. The online participants are missing this beauty, this feeling, but they will definitely enjoy the ambience, the discussion, the discourses, and everything that is going on. That will be going on today and the coming 2 days. Now we will have the second tutorial for computing for cooperative Internet of Things. We know that computing devices, sensors are being installed in many places. Their usage is being increased drastically. The communication and cooperation of such devices are making a huge paradigm shift in human living. Fog computing is a very interesting area in such cooperative Internet of Things. On this topic, we have a renowned speaker, Dr. Rakesh Matham. He is an associate professor of the Department of Computer Science and Engineering of IIIT Guwahati. Let me take this opportunity to introduce him in a bit detail. Dr. Rakesh Matham received BTech degree in computer science from Jawaharlal Nehru Technological University, Hyderabad in 2005, and the MTech degree from Kakatiya University, Warangal in 2008, and the PhD degree in computer science from IIT Patna in 2013. In the next year, that is 2014, he joined the Department of Computer Science and Engineering of IIIT Guwahati. as an assistant professor, where he is currently working as an associate professor and associate dean, research and development section. He is a principal investigator of 2 funded research projects sponsored by the Science and Engineering Research Board and the Department of Science and Technology, Government of India. He is also a member of Design and Innovation Center sponsored by the Ministry of Education. His research interests include wireless networks, IoT, network security, and fog cloud computing. He has traveled long way from Guwahati. Right today in the morning, we warmly welcome him, and on behalf of this house, we request him to come to the podium and deliver the presentation. Let me also inform that this tutorial will be of 1 hour 30 minutes, and we will have question and answer session at the end of the talk. So if you have questions, it will be you will get the opportunity to put forward your question at the end of this talk. So thank you very much. Now I request Dr. Matam to come and present. Yeah, please.
Thank you, Professor, for your warm introduction and invitation. Thank you for inviting me here. So, I will be delivering a tutorial on fog computing for cooperative Internet of Things. This will be a introductory tutorial, so feel free to interact if there is anything that you wish to ask in between. So let me start the talk by showing you the outline of this presentation, and the core idea is of this talk is to make sure that you understand this area by the end of this talk. You must be hearing these keywords, these buzzwords, Internet of Things, fog computing, cloud computing, etc. At multiple places. If you are pursuing research in this direction, then also you might be listening to this terminology, or even if you are working in some other areas, but still these topics are the key buzzwords right now, along with artificial intelligence, machine learning, natural language processing. All these are the key buzzwords where the industry's main focus is on these key technologies. So today we'll be talking about 2 such technologies that operate together, and what is the necessity of their operation, how they come together, and how they increase the usability and effectiveness of each other. That is the goal of my talk today. So this buzzword, Internet of Things, you must be hearing a lot about it. Lot of startups, lot of companies are typically focused around this particular topic, Internet of Things, because nowadays we have seen that lot of things are either pushed as intelligent or smart. So Internet of Things makes these devices smart. So what do I exactly mean by smart is that any device that can operate autonomously, right? We attribute some smartness to that object. So this key technology, Internet of Things, facilitates things to be connected to the internet. As you can see here, the growth of devices that are getting connected to the internet has been rising exponentially, and it is predicted that by the time by the year 2025 there will be 75 billion devices. So on average each person will be having around 8 to 10 devices associated with it. So these devices can be your mobile phone, your laptop. These are the generic computing devices. Along with it, it might be your watch, it might be your smart keychain, all these or glasses, etc. These devices are also getting smart. We have seen multiple examples, like we have a smart air conditioner, smart fridge, or geyser. All these devices are also getting connected to the internet, along with the typical devices like your mobile device and computer. So once all these devices that are connected to the internet, the main purpose of these devices is to continuously monitor the environment, process some data, generate some data, and maybe do some specific tasks that are intended for it. For example, looking at the current temperature of this, if let us say this classroom is an ambient classroom or a smart classroom. So, looking at the current temperature, looking at the number of people that are sitting in this classroom, the air conditioners will automatically adjust the temperature. Right? So, that is an example of how these devices can work. So, basically, these devices' primary purpose is to process the environment, do some specific task that is assigned to it, and carry out forward. So, these devices basically generate lot of data, and sometimes they perform some computations on this data. So the major challenges with these devices are these devices usually are not specifically designed for computation. They are specifically designed for some sensing, mainly for some type of sensing. So usually these devices do not have sufficient processing capabilities. So that is why these devices are usually typically resource constrained. So resource constrained in terms of computational capability, or resource constrained in terms of memory, processing, etc. So what happens when these devices are used for some computations? For example, there are, let us say, a set of smart cameras that are set up for effective security and control. So these smart cameras are monitoring the movements of people in a certain location. So if these devices are provided a computation, like you want to monitor a person of interest using these smart cameras. So these smart cameras are supposed to look for that particular person and continuously monitor. So when this person is continuously mobile, so these smart cameras have to actually transfer the relevant data to the next ongoing, or the next camera that is in the path of that movement of that person. So this can be a simple computation, but these cameras might not be able to process this much amount of media content that is generated through this real-time processing. So what happens is that these devices usually have to rely on some other technology for their computing needs. So the most obvious technology that one can think of to integrate these Internet of Things is with the cloud system. So cloud initially was designed for other purposes, but with the advent of this Internet of Things, the integration of IoT and cloud has become complementary. So basically, cloud has solved the major challenge that these IoT technologies faces, that is resource constraints. So these are the challenges in IoT devices. They are limited in terms of resources, in terms of computation, in terms of energy, in terms of storage, or in terms of data rate. And these devices are manufactured by multiple vendors, so they are heterogeneous, right? For example, smart cameras, let us say, if you simply type for a smart camera on Amazon, you will get more than 100 different types of vendors who are selling the same, selling a camera which does the same purpose. But the hardware that is used on this camera might be different, the software that is used on the camera might be different. So there are heterogeneous types of devices, heterogeneous vendors. The size of the memory available on the device might be different, right? The capacity might be different. So these are all the challenges that are associated with the device. With these challenges comes the issue of security and privacy, which is a common issue that can plague any kind of system. So since the devices have these restrictions, definitely privacy and security is one of the major challenges that the IoT systems face. So to address these basic challenges, you have the cloud ecosystem that can solve all these purposes. Since, like for example, IoT device do not have memory, okay, transfer the computation to the cloud. So IoT does a system that is not scalable, so transfer the operation to the cloud. You cannot process the data, transfer the system to the cloud. So this integration is so evident that there are several commercial available solutions that can allow you to integrate IoT solutions with cloud-based solutions. For example, we have Google IoT Cloud, we have Microsoft Azure IoT solutions, we have Amazon AWS integrated IoT solutions. So several commercially available solutions are there that allow you to set up an IoT application and integrate it with the cloud. So basically, all these devices are directly connected to the cloud. But this, in turn, even though there are a lot of advantages of the cloud, like cloud will provide you with sufficient resources. So IoT system need not worry about whether you have resources or not. It need not worry about whether this computation can be done on this system or not, right? So basically, cloud solves all the problems that an typical IoT system faces. But there are some additional challenges, even though the combination integration between these two technologies is beneficial for both technologies, but there is still a major challenge. What are the major challenges that an IoT cloud system faces is that since cloud is this large capable data centers that are placed somewhere geographically somewhere else, there is an increased latency due to the cloud integration. The cloud may be located somewhere remote, so these devices have to be continuously connected to the cloud. So there is a latency, network latency. So if I send a request for an operation, for me the time taken for me to get the result back from the cloud might not be acceptable in some of the real-time applications. Some applications will not be able to, for example, take the same example of monitoring monitoring a particular person for safety reasons, right? So you cannot rely on the cloud to solve latency intensive applications. For example, there might be an industrial IoT setup where the latency in terms of milliseconds is expected, but the cloud usually has a latency sometimes running in seconds. So this delay might not be acceptable or might not be suitable for all types of applications. And as I said, real-time computation may not be possible, where your delay latency expectation is in terms of milliseconds. And cloud is centralized, so whatever the data that the cloud gets is from in a global context, and sometimes there is a necessity of context awareness, right? For example, the same thing. Let us say I am having a security monitoring system for this campus, right? So I need location specific information sometimes, and I need context awareness in what context it is being applied. That will definitely help us to solve the same problem in a much better way. So that is missing from the cloud component. And usually when all these IoT devices are interacting with the cloud, there is definitely an increased traffic towards the cloud, right? So that will also affect our network performance. So that's why high network congestion may be experienced when all the interactions are going to the cloud. And IoT devices sometimes may not always be able to reach the cloud, because whenever certain location, due to the location disadvantage or due to the coverage issues, sometimes these devices might not be able to reach out to the cloud. Then how to deal with those scenarios? And the same thing. I mean, disconnected with internet connectivity is the same point that I have just mentioned. So these are the challenges with IoT and cloud integration. So that is why once IoT and cloud solutions were coming together, then they realized the need for an additional computing layer in between the IoT systems and the cloud. So that there came this idea was conceived, the fog computing. There are multiple ways of defining fog computing. There are the same fog computing is also referred to as edge computing sometimes, or multi-access edge computing. But there is a subtle difference between all these technologies: edge computing, fog computing, multi-access edge computing. There is a subtle difference, small difference exists. We will define further when we come to that particular use case. So fog computing was the idea was given by Cisco in the year 2012. So the idea was that not to replace the existing cloud computing capability or the existing cloud computing facility, but to provide some intermediate computational facilities for these devices which need real-time computations. Cisco came up with the idea of using certain other networking devices that can provide computing and storage facilities. So basically, it's first started with using the facilities like Cisco switches that were having sufficient computing capabilities and storage capabilities that can perform certain computations. So they, Cisco came up with integrating of all these devices in the form of a distributed computing facility, and that is closer to the end devices. So basically, the architecture of cloud that suggests is that there is a cloud system, cloud layer that is geographically the end layer, means the lowermost layer is the end user layer, which is comprised of all the IoT devices. Anything imaginable, anything small device is present in the end user layer. These devices, in the absence of fog layer, were used to interact with the cloud layer. So the distance between these devices was sometimes huge, so could not satisfy the latency requirements. So they introduced this concept of fog layer. The fog layer is comprised of all these computing and storage devices, either specifically introduced computing and storage devices or traditionally available computing devices like an access point, like a gateway router, which along with its networking functionality can also provide some computational facilities. So more and more generic purpose devices are being used for routing. For example, if I take an programmable device that can function as a router and also can function as a small scale computer. So more generic purpose devices have been used in this fog layer. So the basic functionality or the basic motivation for introducing the fog layer is to minimize the overall latency of the network. So devices close means definitely latency is less. Minimize network congestion, definitely, because it is more localized. The transmissions are more localized, so this device is only interacting with this device. So the transmissions that are going to the cloud is lower now. So definitely the network congestion is lower. Reduce the cost of bandwidth. So any computation that is towards the cloud has some cost associated with it. It can be a network cost or it can be usage of the cloud cost itself. Let us say I am using the Amazon AWS solution for my cloud computing facility. I have to pay them cost for using their facility, right? So if I can do it locally, I can minimize that cost, and also to provide privacy and security. So whenever the cloud is involved, your data is going to the cloud, and the chances of exposure are higher. So to provide localized communication and localized processing will definitely preserve the privacy and also provide you better security. So for example, this is a use case one. Let us say I am using this fog computing setup for providing public safety and security. So there are many such applications. Like for example, we are hosting Commonwealth Games, or like there is upcoming ongoing Asia Cup. So these are large events where that can be used for, means there such type. Is there any property? Okay, so this can be used for, this can be a typical use case for computing solution, right? So basically there is a large gathering of people and you want to detect any kind of untoward event in this large gathering of area. So these are the small, you can see these are the fogs devices that are set up. So with cameras, they are trying to detect people who need some kind of help, or they want to prevent, means if there is any event, they want to divert the people. Or for example, I want to detect people who are having some kind of weapons or some kind of metal items with them, carrying in these large, right? So these can be all different types of functionalities that can be used, right? So now if we imagine developing such a solution without the use of the fog computing facility, what we have to do is we have to rely on the cloud for performing all these tasks, right? A task can be as simple as detecting a person who is having a metal device on him, let us say. That task has to be sent to the cloud, right? So now with the usage of fog, what can happen is the locally available computing facilities can form a layer of devices, and that can offer computing facility and communication facility, and also storage facility. Like the second use case can be in healthcare. For example, you want to monitor in a hospital, you want to monitor patients who are either mobile. Patients can be mobile, they are moving, or some patients can be bedridden, right? You want to continuously monitor their activity. That can also be done with the help of, means that performance of such an application can be improved with the help of for computing, right? So basically, what it provides is it provides location and awareness. It provides you the control over data, because all the data is not going to the cloud, and it can facilitate real-time operations. So this is a typical second use case. There are multiple such use cases. Enormous number of use cases are there. These are the two use cases that I am presenting. So this is the typical difference between a cloud computing facility and a fog computing facility. So latency, only if you are using cloud, then definitely it is higher, then it is lower because of the geographical distance. Architecture is centralized, architecture is distributed. So distributed architecture means associated challenges will definitely be there. Capacity, so basically cloud means there is no limitation. Here there is definitely a limitation. So basically, instead of sending all the data to the cloud, which might not be necessary, so the fog can act as a filter. So location awareness is provided by the fog computing facility. Geographical distribution is supported by fog. The scalability is higher in fog. Number of users in millions, in billions. This is debatable. You can actually scale the fog cloud also to any number of devices. Communication mode. All communication to the cloud is over the IP network. Here the communication can be alternately through Wi-Fi, 3G, 4G, depending upon the application. It can be tailored. So privacy and security is low and high. The reason of argument is that the cloud is mostly centralized. So the data you are outsourcing to some third-party service provider. So that is why we fear loss of privacy. So here the data is handled locally. So that is why we are saying that it is providing higher privacy. So what constitutes a fog devices? It can be as simple as a switch, access point, router. A smartphone and laptop can also become part of a fog device. So anything that has some resources can act as a fog computing facility. So basic functionality of these fog devices is to perform your computations, to provide some kind of transient storage, and some networking functionalities can also be accommodated by fog. Let us say, for example, you want to handle for your IoT application, you want to handle the firewall on the fog facility. That can be done. You want to load balancing facility, you want to implement. That is the networking functionality. You can outsource it to the fog. So some networking and definitely application services can also be hosted on the fog. So, what is a typical operation? What is the typical functionality of a fog device? Sensor devices or smart devices will send some data. The sensed data is sent to the fog node, nearest fog node, for some kind of processing. So, the fog node usually does the processing on behalf of that IoT device. And if the fog node is not able to process that particular computation, its main functionality is to find out where this particular computation can be processed, or if it is not able to find such a location for processing that particular computation, it can outsource it to the cloud, offload it to the cloud. There are multiple architectures for implementing this fog computing. Generally, the three-tier fog architecture that I have already shown, where there is a cloud layer, fog layer, and the end-user layer. And there is a multi-layered or hierarchical fog node placement architecture. There is a helper node-based fog architecture. Then categorized fog node placement such as computing, caching, relaying, and control fog nodes architecture. And there is a centralized fog control node-based architecture. Depending upon the application environment, the architecture finds suitability, and each architecture has its own positives and negatives, advantages and disadvantages. For example, this is the multi-layered or hierarchical architecture. Three-layer architecture I have already shown. This is a multi-layer architecture where the fog nodes are arranged in the form of layers. So upper layer fog devices have more resources than lower layer fog devices. For example, this is an access point. This can be a cloudlet. This can be a small data center, right? So these layer 1 devices can be a typical networking devices. Layer 2 devices can be specialized storage and processing devices. Layer 3 devices can be much more capable devices. And these devices, this is multi-layered fog layer architecture. And you have helper node based architecture. So instead of forming a distributed computing environment, what can be done is that a fog node can have a specific computing facility associated with it. Can be a small commercial cloudlet, which is a typical computing device that can be associated with any networking device, and it will perform the functionality on behalf of this particular device. So these devices will generate data, send it to the task node. The task node will take the help of this helper device to perform your computations. Right? There is a centralized fog node architecture where there is a centralized controller. Basically, this is more suitable for confined environments. For example, you are setting up an industrial IoT network, so you know the boundaries of your network. So strategically, you are already placing your fog devices. Then you can have a centralized controller. Having a centralized controller will help you to manage all these devices all together, and also make sure that the debugging becomes easier and managing of these devices becomes easier. But again, it has its own limitations, and this specific architecture is job-based specific architecture. Means for computing needs, I will rely on one specific device. For relaying needs, for networking needs, I will rely on some specific device. For caching needs, I will rely on some specific device. So this is specific architecture that is based on job based. So what is the typical operations in fog computing along with computing, storage and networking? What basically this fog layer has to achieve is that it has to help you, means IoT devices are relying on these fog devices for their computing needs and storage needs. So whenever there is a computing need, the fog layer has to handle that computing task. So to handle that computing task, what are the major requirements is that how to process it. The task might need some resources. Whether that particular fog node is able to handle that request or not. If that particular fog node is not able to handle that request, what is the best possible location to process the task? So when all the associated problems that are related to handling of a task comes here, that is the task offloading, fog node selection, management of resources, and meeting their specific task requirements. Specific task requirements means, for example, some task will need a specific latency requirement. So it needs the result in meeting some specific deadline. So that is a task requirement. Or for example, the task needs to perform the computation need as much low cost as possible. So the energy spent should be as minimal as possible. So that cost requirement can also be one task requirement. So there are whatever the task requirements can be, that can be thought of. All those task requirements has to be handled by your fog architecture. And then certain security requirements. For example, there might be certain corporate rules. For example, Microsoft does not send any data to the Google Cloud. Right? So that can be a security requirement. So it should make sure that the task is being handled in meeting the security requirements. And sometimes, and also, since we are depending on for our computing needs on the fog environment, then we should be able to verify whether the computations are being carried out or not. So the computation should be verifiable. So verifiable computation is also an operation that should be supported by your fog computing environment. So since everything is centered around the handling of tasks, how to handle the tasks, how to effectively manage them, and in a distributed environment. So means if you are from the systems field, you must have realized by now that fog is nothing but a distributed computing environment. So since it is exactly like a distributed computing environment, what are the major differences between those two? So the major differences is that when we talk about a distributed computing environment, it does not have any kind of limitations. But however, this fog computing environment might have certain limitations, like limitations in terms of computation capability, processing power, or storage, or even energy, power consumption. So we are defining a task. This is a simple definition of a task where the task is defined by a tuple S and C, where S is the input data size or task length, and C is the minimum required CPU cycles that are needed for you to perform the task. So so the computing requirement can be calculated as a simple product of the size of the task and the processing density of that device. So other parameters that need to be considered while defining a task are or while defining the task requirements are deadlines, priorities, arrival times, critical or non-critical status, privacy requirements. So these are the different types of tasks that can be categorized: latency aware, deadline aware, priority aware, or privacy and security aware. These are the different types of task requirements that may have to be handled. So this is a generic definition. A specific definition can vary from application to application. So as I've said, this is a use case and this is an example of a task. Automated robots are moving from one place to another place let us say in an automated warehouse, large warehouse. These industrial automated robots are moving. So they have to detect they have to detect, they have to keep on interacting with other moving devices, and they have to maybe estimate the presence of a device, or they have to estimate the distance from any other moving device. Let us say that estimation itself can be a task. So the task can be to compute if there is any moving object through the use of any motion sensor, to calculate the distance between a robot and the object, right? So, and based on the processing of the task, suitable alerts may have to be generated, right? This is a typical task, and to perform this task, let us say, I need certain task requirements. So that defining the task requirements can be is necessary. So why is it offloaded? Why offloading is necessary? Offloading may be necessary mainly to meet the latency requirements of this task, insufficient processing capability to compute the task, permanent or long-term storage requirements that need to be handled of that particular task, insufficient data to compute the task. For example, I have sufficient capability, but I do not have all the information. For example, let us say this large auditorium has sensors placed along the room. A single sensor might not be having all the data that is necessary to take a particular decision, whether to switch on all the air conditioners or only certain area air conditioners, or air conditioners only in a particular place. Let us say this particular task needs data from multiple sources. That data might not be available. So that also may lead to offloading the task. Insufficient data to complete the task, inability of meeting task deadline requirement. I have computing resource, but using my computing resource, I cannot meet the deadline. To meet requirements of interdependent tasks, some tasks might be interdependent. To provide privacy and security requirements of tasks. All these things may force a terminal node to offload a task. So the terminal node offloads a task typically to a form node. So an efficient offloading mechanism should be able to achieve these three fundamental things. Basically to meet the task requirements, and also to make sure that the fog network is load balanced, and also to make sure that the power utilization or utilization of resources is uniform across the fog network. Because we have defined in the beginning that the fog network is comprised of multiple types of devices, and some types of devices may also are power constrained. So you need to make sure that the its power utilization is uniform. So these are the main three requirements that you need to make sure that your offloading scheme will preserve. So there are various architectures that are available to perform these or handle these offloaded tasks. These are typically classified into 4 categories. One is neighboring, hierarchical, random, and there is a centralized controller. So each have different architecture, means each architecture have different challenges. For example, neighboring architecture, since you are only relying on your neighbors, so there might be an equal possibility that the neighboring particular fog node might be busy at that particular point of time. And hierarchical, it causes inefficient resource utilization and load imbalance problem. So it doesn't mean that architecture is completely not useful. It is useful only for certain cases of applications. For example, when means in hierarchical, as I already discussed the hierarchical model. So there are hierarchy of fog nodes. So once the lower hierarchy of fog nodes cannot handle the task, only then the higher hierarchy node is with the fog, the task is offloaded to the means a higher level. So usually what happens is that the offloading basically maintains that tries to solve the task in the lower layer, and only when it is not feasible it is sent to the higher layer. So sometimes the performance degrades. And this random model basically is trying to offload tasks to a random set of locations. and there is centralized architecture. So centralized architecture typically inherits all the problems that are associated with the cloud. So these basic issues are considered while you are designing a task offloading scheme. One is the selection of the fog node, heterogeneity of the tasks, whether the fog nodes and the terminal nodes are mobile or not, and how to balance resources across the fog network, and finally the privacy and security of the fog nodes. Right? For example, these are the various ways in which a task can be offloaded. For example, terminal node cannot perform the task; it is sending it to the primary fog node. Primary fog node cannot perform secondary fog node. The primary fog node cannot perform, can send it to the cloud. Secondary fog node cannot perform, send it to the cloud. Right? So, like for example, here a user has asked for a request from the terminal node. So the terminal node basically is not able to meet the task requirement, so it offloads. So this particular primary fog node further offloads. So either the offload decision can happen here or here. So if it happens to the cloud server, the results are here, or if it happens here, like that. So anyways, the results are ultimately that the user is supposed to be served for that particular task. So these are the various ways in which the particular task can be handled. So this I have already specified, means we are dealing with the selection of a particular fog node, and that particular selection is based on the availability of resources on that particular network, fog network. So a typical offloading schemes, how a typical offloading scheme works, based on the task requirements, a terminal node decides whether a task can be carried out or not. If the terminal node cannot perform the computation, it offloads to the primary fog node based on the parameters. The primary fog node computes the location where the task needs to be handled. So we have specified that there are 4 architectures, that is neighboring, random, centralized, hierarchical. These are the 4 models in which the fog computing environment can be maintained and can be set up. So all these things are dependent on one particular factor, that is, I need to know what is the resource availability status across the fog network. Since it is a distributed computing environment, so the availability of resource status is gathering the resource availability status across the fog platform itself is a major challenge. So basic need is that I need to find out what is the status of the fog network. What is the status of the fog network? Means there might be, let us say, 100 nodes, 100 fog nodes. So each node has to, so it is dynamically performing its computation. So each node has to determine, each node has to allocate its resources, and based on these resources, I can decide where I can perform this particular computation. So the 2 major problems that need to be addressed are how to acquire this status. How to acquire this status, because it's a dynamic environment, it is a challenge, and how to maintain this state. How do I report this? Which, for example, I am a fog node. I have, let us say, this much amount of resource at that particular instance of time. How do I report this data? Do I simply say that I have this much processing capability and this much amount of memory can be spared for this? Is it sufficient? Or certain other factors need to be considered or not? That is the major question that we need to answer. And network reconfigurations, because of the dynamic changes in the environment, network reconfiguration has also to be handled. So how to handle those changes in a fog environment? Is do the typical static mechanisms, right? For example, let us say we are maintaining network of this particular institute. If there are any changes to the network, that has to be done manually. Is that similar methodology will be useful or will be applicable to fog environment? Yes or no, that we have to find out. Task migration to handle mobility and failure. Right? So these devices itself might be mobile. For example, take the example of a smart traffic light management system. So it depends upon several factors. It depends upon the current. For example, if the traffic is low, the duration for the red light, green, and means the time gap is dynamically changing. So it depends upon several factors. It depends upon the context. It depends upon the time of the day at which those lights are functioning. For example, early morning 4 o'clock. It did not wait for entire 1 minute. Let us say traffic lights or street lights. If the pedestrians are moving, they should dynamically come on and off, right? So here one of the nodes are moving. For example, here the user is moving. So how to handle mobility? So mobility has to be handled in multiple ways. Can be handled in multiple ways. One way is that the entire task is sent. Another way is that the task that is under process has to be migrated. When the process has to be migrated, there are several other challenges that arise, because it is a continuous operation. So how to migrate this without losing the data, and also make sure that you are meeting the task requirements. So various ways how to handle that.
Sorry, excuse me.
Yes.
In that case, if the nearest neighbor node gets the information that some node is moving out,
Yes.
so instead of maintaining all those things, only the nearest neighbor node can pass the information. It can send the mobility nodes information in this vicinity.
Yes, definitely. So for that, what here we are assuming is that we know the direction in which the particular user is moving. So we have the direction for that mobility. So directional migration can also be done, or directional when we know the speed in which direction the user is moving, we can specifically migrate or even offload that particular task to the neighbor. So that particular, depending on the application, yes, what you have suggested might work. So here the challenge is that when for some straightforward application, simple application, it might be possible. But imagine that that particular neighboring form node is not only handling the pedestrian movement, but it is also responsible for real-time screening of let us say it's a multi-purpose camera, security camera. So it is doing some other job, right? So at that particular instance, it might not be able to handle this particular job. So all these examples are related to specific use cases. So for the use case that we have said, it will definitely work, provided it is the only job that it is doing, and we know the direction of the mobility. And lastly, we have secure computations. So, all the four models that I have mentioned here, they assume that I have all the information that is necessary for me to take this decision of where to send this particular task for computation. So this is not a very valid assumption. So determining of this false state, that is why it becomes an important challenge. It is still lot of research has to be carried out, and most of the works in this direction or make lot of assumptions. So global state of the fog network is a collection of individual statuses of resource availability of all the fog nodes in the network. So as I said, the need for global status is because only when I have this information, then I can take this effective decision of where to offload this task. So what is the benefit? As I said, acquiring of the global state or the fog network significantly benefits choosing the best suitable fog node, which further benefits lowering the overall latency. Means all the task requirements can be met if I am able to decide which is the best place for me to offload this task. So how to do that? Basically, the selection decision is based on the information that is available about the resources of all the fog nodes. Most, as I said, most of the works in this direction have assumed to have global state and are only dependent on the neighboring fog node status. So basically, instead of having the complete status, I am only dependent on the partial status. So it's like we can see the obvious research gap, but again the argument is that it is why it is not being done is that it is generally quite challenging to maintain the status of this fog network across if the network is comprising more than, let us say, 1,000 devices. It is typically not feasible. It is not scalable at all. Let us say every 5 minutes I will start this data. So this process itself collecting will be so cumbersome that it is not possible. So that is why most of the existing solutions assume some information, right? So, but assume that the information itself has some challenges, as I have already pointed out. So, two major directions there are: assuming having global state, and also saying that neighboring only subset of fog nodes. So, some of the related work for fog node selection and task offloading is categorized as randomized, neighboring, and centralized controller. So there are some alternate approaches. We are working on one of the alternate approach where keeping the fog node network size to a reasonable area. We have experimented with this alternate architecture where we have grouped a certain set of fog nodes into a clusters, and what we have done is we have chosen a particular node as a cluster head, and we tried to maintain the status information is shared among only these fog nodes. So as I said in the earlier slide, the major challenge is keeping that interaction among lot of devices, which is definitely a challenge. So we tried to solve this problem using this alternate approach where we have divided the fog network into clusters, and we try to manage interactions between only these cluster heads. So the status information is maintained by these cluster heads. So whenever a particular fog node has to offload this particular task, it will offload it to the nearby primary fog node, and that primary fog node, with the help of this cluster head, will be able to find a suitable location to transfer that particular task to any of the cluster head, right? So that is the first experiment that we have carried out.
So what will be the cluster heads?
What will be?
What will be the components in the cluster heads?
Basically, cluster head is nothing different from the regular computing fog node. The only thing that while experimentation what we have assumed is that the cluster head will have reasonably better resources compared to the other existing fog nodes.
So cluster head is totally centralized.
Of course, means you can say that. You can say that it is working as a centralized again a centralized model. But the thing is that any device can take up the role of a cluster head. It is not unique to this particular device. Only for representation purpose we have shown it here in this way. Any device can take up the role of a cluster head.
But if the cluster head is compromised,
of course, security related issues definitely will be there, and here when our aim of providing an alternate approach is that is it computationally feasible for us to gather this global state and maintain the status of this fog network. Let us say my particular fog layer will have 1,000 devices, for example. So I will not be able to scale this architecture to that model. So this experimentation has definitely certain limitations, but this is an alternate architecture to whatever the existing models are there. So I have discussed 4 models, that is neighboring, hierarchical, right, and random and centralized. So this is kind of semi-centralized, you can say, right? So here this cluster head is doing some operations. So instead of all these devices involving in the exchange of resource status information, only a subset of devices are maintaining right? Now that can also be addressed in the next slides. I will say that what could be the problems with this type of approach and how these can be solved. I will show you in the next slides. So how this global state can be maintained is that, for example, very simple yes no kind of flow chart. If the device can complete the task, no, then offload it to the primary fog node. If it can, yes, then compute it a task J. Otherwise, and means computed a task J, inform the status, means update your resource availability status to the cluster head. If not, offload it to the cluster head. The cluster head will have to determine where that particular task can be computed, and ultimately, basically, the information is always updated to the cluster head. So the cluster head will have the latest resource availability information. So in that way, basically, we are able to find a appropriate location for handling that particular task. So how to determine the status of each fog node device? We have incorporated certain parameters that can reasonably tell us what is the status of that particular fog device. We basically considered the next availability, means what is the next available service time instance. We have considered available computational resources, available energy, memory, storage, etc. Generic model, right? This can be tailored to some specific things, definitely. The service time basically is computed as like current, what is the fog node currently what is computing, and what are the number of tasks that queue is currently executing, right? So what is the amount of transmission time? That depends upon the size of the task, means data rate, and what is the size of the network packet. Energy consumption status, we have considered these different parameters like transmission, reception, computation, idle, sleeping. All these different energy parameters are considered. Available memory status, similarly, available memory status is computed. And what is the needed memory status to perform that particular task. So idea is that whenever you are handling a particular task, then definitely there are certain parameters that are associated with it. How to get a generic overview of what is the current resources that are available at that particular node or station. So available storage stations similarly, and that is dependent on if certain tasks require additional storage capacity for storing the data, for storing specific results, right? So it all depends upon definitely the type of task. Excuse me. So now the alternate approach that we have shown is that each fog node in this particular model will be able to report the resource availability status, but that itself is a problem. That itself is a problem mainly because this is dynamic environment. Today, now I say that I have this much computational capability, or I may say that this much resource I can spare for offloaded tasks. Since the tasks are dynamic, a time instant t I have shared, a time instant t plus 1, it will dynamically change. So the resource availability status, since when it is dynamically changing, the offloading decision that you are making is definitely not going to be performance optimized. So this itself is a problem. So alternate approaches have been designed. One is the resource availability prediction. So you are having the resource availability information of all the nodes for certain duration of time. So you can use certain either machine learning models or some kind of stochastic models to predict the availability of the resource. So when you can predict the availability of resource in future, then your current offloading decision can definitely be based on that particular factor. So then the obvious next direction to handle the problem of resource availability is the resource availability prediction. So hence there is a need for a proper resource availability model which provides knowledge about the future availability of resources in the fog computing environment is the necessity. And also, how to even represent the resource availability information. The resource availability information might be certain data structure, right? It should have certain components, like let us say how to represent the, because devices are heterogeneous. When I'm representing my particular available resources, it might be different from some other devices. So how to maintain that information as such? Should we maintain a simple table? Or should we, there need to be any specific representation structure that will help us to not only predict but also to maintain that information. So that itself is also another research problem that very few research has been carried out in this direction also. And the next obvious step, or I am saying obvious because I am saying that these are all interrelated. These are all interconnected. Once I solve the problem of resources, and once I solve the problem of availability of resources also. Now, the next obvious problem, or the next problem that one needs to solve is that what happens today. Let us say I have a security camera that is only handling the job of finding out a particular, let us say, temperature of a person, right? So there is a thermal camera that is installed, it is finding out the temperature of the person. Tomorrow, it has to find out something else. So that if you want to support new service on that particular device, that new service has to be supported, means you have to install that new service on that particular device. Only then that service will be up and running. So let us say there are 1,000 such devices. On each device, if you have to manually change or manually add a new service, it's not scalable. And typically, all these applications will have dynamic requirements. For example, we keep talking about smart cities or smart showrooms, right? All these are use cases. Smart city. Today, the need might be this. Tomorrow, the need might change. How to handle dynamic applications, dynamic services? The existing fog computing environment cannot support. Simply, it cannot support it. It can maximum can handle. That too, you have strategically placed, strategically said that this is a particular job you have to do. It is able to handle. Beyond that, it is not able to. So how to change this fog computing environment so that new tasks can be supported, right? Which is not feasible with the static network support. Also, it is quite difficult to change network configurations. Let us say I have configured my fog network to make sure that if this particular job is to be executed, this has to be routed through this particular high performance path. Now I have changed the task itself. So the paths also need to be changed. So the simple network setup might not be able to handle this, right? So there is a talks of using software defined network setup, controller based architectures. Thus, IoT fog environment reconfigurability becomes necessary to handle dynamic application services, network settings, configuration parameters, etc. Right? So the next possible way of doing it or handling this problem is SDN, software defined networking, and programmable approaches to solve this problem. Like so as I said, we have come up with that alternate approach of gathering resources and trying to offload tasks. So then we figured out that this is not sufficient because these nodes will keep on changing, right? And with the change of resources on the nodes, then definitely the services might also change, right? So then we have experimented with a dynamic network setup where we have created certain set of edge nodes, certain set of core nodes, some access points, and we have provided some programmability on these devices. Means we made sure that these devices can be over the air programmed. So we made a programmable controller. We called it as a Pro Edge controller, and we experimented with this setup where we had some sensor devices, actuator devices, some motion sensors, and certain set of nodes, right? So using this controller, what we could achieve is that we could dynamically add new services, dynamically alter routing configurations, and dynamically manage this entire network. So this is one possible direction that can be used to handle dynamic changes in the network. So industrial means we have designed this keeping in mind the industrial IoT network setup. But the same model can be applicable to any kind of network setup. So here we have considered a backplane of SDN backplane, and we have assumed that the edge devices or the fog devices are programmable. So using this Pro Edge control, we had a controller that can actually control the tasks on these devices. We can add and remove or make changes to the existing tasks, and these tasks. So the end devices that are connected to these edge devices, they can, let us say, it has asked for a new task 2, right? For example, as I said, now instead of temperature, I want to measure the humidity. So the task is not present in this edge device. So using the programmable edge, I can make sure that that particular task management application is there in this particular edge node, and it can dynamically meet the task requirement. So basically, the terminal nodes now are relieved of the headache that I can only do this type of task. No, dynamically can be changed. So it is suitable for an industrial IoT network or a smart building where services can be added. So there are several implementations like it can be managed through microservices also. There are several practical implementations of fog like IO fog, Cube Edge. Those can be used. So a need for fog computing architecture that can support improvised or new services dynamically. That is the next possible issue. And the next possible issue that the fog computing environment has to handle in a cooperative fog computing environment is offloading of tasks. It's not sorry, mobility of fog devices. Right? So user mobility. So here the problem can be addressed in two ways. One, the user is mobile, but the task can be performed at a single device. The task can be means I have certain job. Let us say I have a job of sorting a large array. That is a simple job. That job can be done. That completion can be done anywhere. I as a device is not able to, but can be done on any device. Let us say I want to find out what is the possible path, means route that I have to take to reach a particular destination, which do not have toll gates or which do not have certain parameters, right? So that can also be a task. I have given it the task to reach, right? So the task can be handled by any of the single fog device. However, the device is mobile. So that can be handled using static mobility case scenarios. And sometimes the task is continuous. Let us say, what I mean to say is that a user is moving and his task requirement is dependent on continuous stream of data. If its task requirement is on continuous stream of data, it cannot be solved using a simple request response model. It cannot be solved. The mobility cannot be handled using a simple request response model. So what happens in that particular use case is that the tasks have to be migrated. Means the task is currently executing and it has to be migrated in operation. So two different use cases are there. So how to handle it in mobility aware fog computing? The terminal nodes can be mobile. The fog nodes itself can also be mobile. Both devices can be mobile. So the nature of mobility can also be dependent in multiple ways. mobility can be dependent, mobility might be random or directed mobility. For example, the example that we have asked is directed mobility, means I know that the particular user is going to travel from this particular location to next particular location with this velocity in this direction. So directed mobility. For handling directed mobility, then it becomes easier, mainly because if certain parameters are known, then I can estimate the location where the particular user will be after a particular duration of time, right? So handling directed mobility is easier. Random mobility, it becomes different. A random mobility is only mainly because when the use case is random or the situations are dynamic. So I said migrations of task becomes essential in one of the two possible scenarios, to accommodate mobility of users and to accommodate failure of fork node, of course. So you have given a job to one particular fork node and it has failed, right? So then either if it has failed, then it has to be handled totally differently, or suddenly due to some certain scenario the task cannot be progressed further, so it has to be migrated. So migration also, there are several literature already exists. There are certain mechanisms. So there is some cost that is associated with migration. The cost is in terms of network usage, latency, energy consumption, cost of execution, etc. Right? All these have to be considered, and based on the migration strategy can be a proactive strategy, means you are already estimating that migration might has to happen, reactive and hybrid, combination of both. So the initial set of problem, the initial part of the problem where the user is mobile, but the task can be handled by performing computation at one particular location. That part of the problem we try to address that particular problem. So what we the solution was basically centered around handling the means detaching the device mobility with the job of performing the task. So we have that can be further handled at three different levels. If the task is computed by the primary fork node, the task is computed by the secondary fork node, and the result is sent to the primary fork node. That means the device has not moved out of the range of that particular fork device, and the task is computed at the secondary fork node. Result is collected by the primary fork node and forwarded to the fork node where the particular user is now, is based on its current location. So this also we have detached the complete need to maintain the mobility status of the device. Basically, we made it by allowing the user, which basically the user will ask for its result, and this particular fork node will fetch the result from wherever the job was executed. So that was one way to handle mobility. The another way to handle mobility is directed mobility, where we predict the location of the device. Using certain learning algorithms and try to offload to the nearest location where that particular device is moving. And the last issue that needs to be considered in terms of addressing the issues related to cooperative for computing environment is the issue of security and privacy. So to summarize, basically we started with how to handle tasks, offloading, what is the problem with existing architectures, what is the need for new architectures, how to handle resources, then how to handle dynamic services, how to handle mobility, and lastly we are concluding it with the importance of security and privacy. Right? The computation at the end user devices can assure the user's privacy by not sending all the data to the internet, that is the cloud. So basically we have seen multiple examples of news of data getting leaked through cloud servers of Apple due to user settings, due to cloud settings, and in some cases, the cloud service provider might be, because since this data is valuable, the cloud service provider might be selling the data without the knowledge of the user. So there is always a possibility of user data being compromised or being shared with unknown entities. So the best possible solution is that not to send the user data to the cloud at all, or minimize basically, right? So especially in the fog environment, offloading tasks to untrusted fog devices may also lead to privacy and security breach. So here, when we say that we are offloading, we are making the assumption that I am giving him the job, he will be doing it and giving it to me. What is the necessity of it? May not be true at all, because the fog device might be compromised, or he might have incentive in keeping the data, part of the data, right? So there are multiple such scenarios that can crop up. Fog computing requires an adequate mechanism to verify computational results from untrusted devices. So, how to maintain control of the data when we are dealing with such a untrusted environment? So, when we are handling privacy, the devices may demand secure storage. Right, so basically the fog device may have to give some kind of proof that this device, the data that is being stored on that particular device, will not be shared or cannot be shared with any other. So if the user is able to encrypt the data remotely without the involvement of that particular fog device, right? So there are multiple different ways have to be thought out how to handle this particular problem. Certain scenarios I will try to elaborate here. How to handle authentication, fog nodes, joins, and fog node leaves. This is a dynamic scenario how to handle such type of use case. To access the services of a fog network, a device has to first become part of the network by authenticating itself to the fog. So how to handle dynamic joins and dynamic leaves? Formidable challenge as devices are constrained and mobile. Can authentication be offered as a service? This is certainly an open direction that can be thought of. So instead of me doing the authentication or me providing the details, because since the IoT devices we are saying that they are constrained, I will provide some information to somebody. He will do authentication on my behalf. So based on my information, the authentication should be able to carry out. So is it possible to do that? Is something can be explored. That will be very much suitable to this environment. Trust management. Authentication only establishes initial level of trust, but these interactions keep on happening for over a period of time. Should means the question arises: should authentication be mandated every time I ask for some service? If that is the case, what happens is that then the latency will increase. Right? So frequent interactions need a trust model to reduce the complexity and conserve energy. So can services be categorized to increase safety? This is a research question that has to be answered. And I am trying to summarize these research questions based on a lot of literature. So you can safely assume that very little work has been done in this direction. Secure communications, IoT device security challenges with fog computing environment. Securing communications between constrained IoT devices and fog. IoT devices can request for a service with any fog node. How to handle key generation and manage them. Right? This also can be it has to be studied. How to lower the message overhead to handle dynamic joins and leaves. IoT devices may not be aware of fog existence. Secure communication becomes a challenge. What do I mean by that is that IoT devices do not know where that particular computation is being handled. They are only just offloading it. So how to handle such? If we know that my message is being received end party, I know, then end-to-end communication can be secured using some kind of higher level encryption mechanism. But if the fog, if there is an intermediate layer, and I don't know whether this particular computation will be handled at the fog layer or it will be handled at the cloud layer. I don't know. I'm just offloading the task. So in that case, it becomes much more challenging. So privacy, similar to the security of communications, privacy also becomes a challenge. Mainly because fog node, even though it provides location awareness and context awareness, but still the same thing can also result in a challenge, because I am sending my data to the nearest, so my location is always getting disclosed. How to anonymize, that can also be a requirement, right? For example, there can be side channel attacks that can be possible based on some information. I can understand that this is this particular person. So how to handle location privacy, etc., is a major challenge when it comes to privacy in IoT for computing environment. So this is a complete picture. All those things put together, security and privacy challenges put together. Whatever I have discussed in the previous slides, I will just make a quick conclusion. These are the different research directions that can be pursued in this particular field. Task sharing, reusability, fog node consolidation, scaling, application specific management issues. Application modeling itself can also be an issue. Interoperability and federation of fog failure management. Artificial intelligence based application and resource management. All these possible directions can be taken up. These are the conclusions. Centralized cloud computing facility cannot satisfy novel challenging requirements of a distributed world. Cloud computing facilities are to be extended to the edge of the network. That is why there has been fog computing idea, edge computing, multi-access edge computing, etc. Many different applications of IoT, machine to machine, AR, VR, streaming applications have very specific task requirements, and that cannot be rendered by the cloud. So fog is here to stay. Fog is majority of the upcoming applications will be centered around this architecture. So issues related to task offloading, resource management, device mobility, security and privacy, etc., are to be addressed to enable a quick adoption of fog computing solutions. So, the possibilities are endless. These are high level, very specific directions that one can take up, and one can dig into multiple issues and can be taken up. So I conclude my work here, my presentation here. So these are some of the references. My presentation will be available. I have used multiple images from the internet, from several people. So I am acknowledging all of them. I cannot acknowledge individually. So some of the content here might be copyright. So since we are using it only for educational purpose, I hope that is okay. I will be willing to take any questions that you have. And I guess I'm on time.
Yeah, thank you so much. This is question and answer time. I hope there will be questions. We can also take questions from online participants,
If there are any.
if there is any.
So, sir, basically in IoT or fog, device security and data security is the prime concern.
Yes.
And probably, as far as my knowledge is concerned, no specific solution is yet developed for solving that device security. And especially for the skills that you have presented, or architects are something developed. And I found from your explanation that none of the four architecture is quite secure. So in those architectures, is it possible to apply some artificial intelligence based technique, but with the security mechanism, especially for putting the inputs?
Yes. Is your question done? Yes. See, let us say that I have to implement a fog computing environment for a specific industrial application. So let us think it in a very fundamental way. What will be the first step that an industrial means that particular industry will do is that they will reach out to a particular company. So they will reach out to a particular company. Let us say Intel. Intel has some specific IoT products that have all these specific device constraints, device security embedded into them. There is a trusted environment, trusted working environment. So if all my devices are of a specific brand, specific company, then and my IoT devices are also from a specific company, then definitely the problems that you are talking about can be addressed. It is not that there are no industry-based solutions. There are industry-based solutions. I think Intel SGX. There are certain industry products which address these specific device security and communication security problems. The problem comes only when the devices are not belonging to a specific particular product or a particular company. When heterogeneity comes into picture, then all the problems that you have said will come into picture, and definitely machine learning and AI can be used as a possible solution to make sure to identify or to secure, not only in terms of communication, in terms of device also. The device itself has to be secure. That means that storage on the device has to be secure. Multiple problems will arise. So there are products, but still there are a lot of problems. So what are the problems you have mentioned? They are all still very much open.
Any more questions? Dr. Matham, I have one question.
Yes, sir.
You have basically given a detailed background and very lucid discussion. What I'm curious to know, you can give maybe a couple of applications that the traditional cloud computing will not be able to address, but the fog computing will be able to take care. So maybe a couple of applications. Yeah. if you can.
So here our problem is that cloud can do everything for me. Cloud can do everything for me because I can tailor my cloud for my requirements. I can tailor based on my requirements. Cloud can be tailored, but there are some specific applications which need certain properties that cloud will not be able to satisfy. For example, speed. Cloud once the task has reached the cloud, it can perform as fast as possible because there is a dedicated data centers. They can perform your task and give it back. But the time required to reach the cloud is not acceptable to me. In that particular small domains, these fog will fit. So fog is not to replace cloud; it is just to complement the functionalities of cloud.
Okay. Thank you so much.
Thank you, sir.
Your discussion was really a lot of full of information, and I hope we have benefited quite a lot.
I hope so.
So, on behalf of the house, we sincerely thank you.
Thank you
so much.
Thank you so much for giving this opportunity.
Thank you. Yeah, please have a seat here.
Thank you so much, sir, for the informative session. I request Dr. Mollah, sir, to felicitate our speaker, Dr. Matam.
Let's go there in front of the camera. Yes.
Thank you, sir. I request Professor sir, to come and felicitate our chair,
Thank you.
Thank you everyone for your kind cooperation.